Hi, good morning, everybody. Firstly, I hope everybody can hear me loud and clear this morning. I'd like to welcome you this morning to the webinar from Pilz, Understanding ISO 14119, Interlocking Devices, presented this morning by myself, Jason Reed. I'm one of the account managers here at Pilz. You can type questions using the toolbar to the right side of your screen, and my co-host Alex Bryce and Mark Staples will try to answer any questions that you may have during the webinar. If for any reason we can't answer them during today, then we'll get back to you shortly afterwards. The webinar is being recorded, and a link to the recording will be sent to you shortly after the webinar has concluded. The presentation is also available for you to download during the webinar itself, and that's in the handout section. And I think you'll also find that there is a PDF kind of presentation on like a snapshot of 14119. I'll also point out that any product references today are going to be in the colour yellow and by Pilz. So the agenda today. The agenda for the presentation will be as follows. So there'll be an introduction to ISO 14119, when it came into force and the structure. I'll talk about fault masking or masking, how it occurs, how you can quantify its impact on diagnostics coverage, an achievable performance level, and importantly, how you can overcome it using various means and technologies. I'll run through the different types of interlocking devices as it currently stand in the current standard, and I'll run through measures to prevent defeat or manipulation of the interlock. We'll also run through fault exclusion and what is meant by guard locking. So BSCN ISO 14119 came into effect on the 30th of April 2015. On the 11th of April 2014, the European Commission published EN ISO 14119 in the official journal as a harmonised standard of the Machinery Directive, and as a successor to the previous standard, which was EN 1088. And you can assume so presumption of conformity to the Machinery Directive came into effect on the 30th of April 2015. So the standard is relevant to anyone that manufactures interlocking devices or uses interlocking devices, so OEMs and end users. And in this presentation I mentioned the Machinery Directive. However, now the UK has left the EU, it would apply to the supply of machinery safety regulations. As I say, it's mentioned as known as BSEN ISO 14119. So how is the standard structured? I'll run through the clauses here, but I'll go into more detail on some of them as the presentation goes along. So clause 1 is the scope. Clause 2 is normative references, and that makes reference to other standards such as 13849, 13857, 14120. Clause 3 is the terms and definitions, so that's kind of a glossary. Clause 4, operating principles and typical forms of interlocking devices associated with guards, and we're going to look at this in more detail when it comes to the types of interlocks. Clause 5, requirements for the design and the installation of the interlocking device with and without guard locking. Clause 6, selection of interlocking devices. Clause 7, designed to minimize defeat possibilities of interlocking devices. And so this is where a motivation of defeat for the interlock, and we'll discuss this in more detail. Clause 8 is control requirements, and clause 9 is information for use. And as always, but the back end will be the informative annexes. So again, they'll go through the types 1 to 4. There'll be examples of other interlocking devices, examples of guard locking devices, application examples of interlocking devices used within a safety function, motivation to defeat, and examples of maximum static action forces. So fault masking. So fault masking is mentioned in Clause 8, control requirements. Clause 8.6, logical series connections of interlocking devices. So logical series connections of interlocking devices means for normally closed contacts wired in series or for normally open contacts wired in parallel. When interlocking devices with redundant contacts are logically connected in series, the detection of a single fault can be masked by the actuation of any interlocking device logically connected in series with a defective interlocking device to the safety rated control system. It is foreseeable that during the fault finding or troubleshooting process by the operator, one of the guards whose interlocking devices are logically connected in series with the defective interlocking device will be actuated. In that case, the fault will be masked and the effect on the diagnostics coverage value shall be considered. For a series connection, the maximum diagnostics coverage, DC, should be considered. And note ISO TR 24119 deals with the logical series connection of devices. And 24119, safety of machinery. So there's evaluation of fault masking serial connections of interlocking devices associated with guards and potential free contacts. This is a technical report that is dealing with specific case on how to deal with the serial connections of interlocking devices and the influence of the diagnostics capabilities of the safety function. So the diagnostics coverage is equal to the ability to detect dangerous failures expressed as a percentage, and we'll go through more on that later. So what does this look like in the flesh? And the next following slides are going to show how fault accumulation can happen. So in this example, we have 3 gates all wired in series, as you can see here, and all back to a safety relay. And let's say this is a food production hall with a shift washdown. All guards are closed and the safety relay sees no issues and the machine can be operated. For some reason, the operator needs to open guard 1, which you can see here. It may be due to a batch misalignment, let's say. And when guard 1 is opened, channel 1 opens, but channel 2 is defective and remains closed. The safety controller switches off to stop the machine, and the machine is in a safe state at the moment. But we have to point out that it's safe at the moment. Once they've cleared the misalignment, the operator then closes the guard, but channel 2 is still defective. The safety controller does its job and detects the fault and prevents the machine from restarting. Again, the machine is in a safe state at the moment. Due to time pressure, or knowing how to overcome the guard 1 issue from, say, prior experience, but not necessarily understanding the safety repercussions, the operator then open guards 3. When they do this, channel 1 and 2 both open, which is what the safety relay is looking for, and thinks the fault is cleared. The machine is still not in operation. Guard 3 is now closed. The channel 2 fault on guard 1 is now masked. The safety controller is enabled and the machine can be started with the masked fault. So due to the washdown scenario at the end of the shift, over time, channel 1 on guard 1 also fails, and this could be due to water ingress. The safety controller is enabled and the machine can be started with a fully dysfunctional guard. Now, when guard 1 is opened, the safety controller does not recognize the guard state due to the failure in the 2 channels. The contacts remain closed and the machine continues to run with the guard open, and this is a complete loss of the safety function. So how can we control the likelihood of a loss of the safety function? Well, the likelihood of a loss of a safety function is made up of many contributory factors. So it's a bit like rolling a dice as to which could potentially fail. We have the architecture, which we'll discuss a bit more, which is category B, 1, 2, 3, or 4. We have the detection of the faults to be able to react to the fault, which is the diagnostics coverage. And diagnostics coverage comes from functional safety standards, of which there's many. However, for machine safety, we use 13849. We have the reliability of the components used. We have common cause failure, CCF. So failures of different items resulting from a single event, where these failures are not consequences of each other. And the chance, so what we're highlighting here is that you also have systematic failures. So again, these are very important, but they're not quantifiable. They're down to human error. So that could be when you're specifying parts, it could be the installation, etc. But generally, these are managed by a process of validation. And what we should point out is that the detection, or the DC coverage, and the diagnostics coverage and the category architecture are inextricably linked. You can't have one without the other. And the chance of a dangerous failure is not only based on the reliability of one component, but it depends on the total loop. So all the parameters which we design are effective on the total calculation. It depends on the whole structure. Diagnostic coverage measures the effectiveness of diagnostics, which may be determined as a ratio between the failure rate of detected dangerous failures and the failure rate of total dangerous failures. And bear in mind that diagnostics coverage can exist for the whole part of a safety-related system. So, for example, diagnostics coverage could exist for sensor and/or logic system and/or final element. So architectures. So BS EN ISO 13849 stipulates how a safety function should behave in the presence of a single or multiple faults by way of categories. So category B, the safety function can be lost in presence of a single fault, realized by a single channel and use of basic safety principles. Category B, as with category one, as with category B, safety function less likely to fail due to use of well-tried components and recognized standards, proven use, and well-tried principles. So this could be over-dimensioning. And again, it's single channel. And category two, as with category one, safety function less likely to fail due to the use of well-tried principles of automatic periodic testing. So to detect failure before or on demand of safety function. And again, it's single channel. Category three is a single fault ideally detected won't cause loss of safety function. The second fault can cause loss of the safety function, has a redundant structure and some fault detections. So it's dual channel. And finally, category four, neither single nor accumulated faults cause loss of the safety function. And single faults must be detected with extreme certainty, redundant structure, and very effective fault detection. So again, it's dual channel. So diagnostics coverage, the ability of a safety function to detect within itself a dangerous failure, which could cause a loss of the safety function. It's expressed as a fraction or a ratio of the dangerous detected failures versus all dangerous failures, detected and undetected. And the range thresholds are described in 13849, and the coverage is none, which is anything less of 60%, low, which is between 60 and 90%, medium, 90 to 99, and high, which is anything over 99%. And DC coverage, diagnostics coverage, is all dangerous detected failures divided by the sum of all dangerous detected failures and all undetected failures. So how a category, diagnostics coverage, and mean time to dangerous failure relate to performance level? Figure 5, which we have here in 13849, we have the y-axis, which is the performance level, A to E. We have the x-axis, which is the category level and the diagnostics coverage. And this is why they're linked, because you can't have the category without the diagnostics coverage. Green being low, yellow being medium, and red being high. So this chart is intended mainly for designers to evaluate how they could achieve a desired PL. It's not intended really to verify which PL has been achieved. And so if you want to achieve performance level D, then you really need a medium diagnostics coverage for Cat 2 and above. And this can be impacted by fault masking. So what was discussed earlier, TR24119 addresses the impact of fault masking, and it uses a simple method to look at switches. And so what we have are 3 columns. Column 1 is the number of frequently used movable guards. By frequently, we mean it's opened at least every hour. We have then the number of additional movable guards and the maximum achievable DC. So if you've got no frequently used movable guards, so you might have a guard that's opened every 2 hours, but you've got an additional say 2 or 3 guards again that are opened every 2 hours, then you've got medium diagnostics coverage. If you've got 1 guard that's opened every half an hour, let's say, and then you've got another guard that you may open, every hour, again, that's medium. So as soon as you have 2 switches in series, then the maximum DC you can achieve is medium. And in any case, if multiple movable guards will be opened at the same time as part of normal operation or service, say to clean the machine down at the end of a production run, then it's foreseeable that fault masking will occur and the diagnostics coverage is limited to none. So we've determined that fault masking is an issue. So over the next few slides, I'll show different ways of how you can overcome it. So one way is independent circuits back to the panel. So you can individually wire interlocks and other volt-free devices such as e-stops directly into the individual safety relay or modular safety relays and create hardwire logic without software between the safety, and you can kind of tie in between the safety relays as required. And if need be, you can tie them together, and so that the final output would be to stop your motor, for instance. And so for Pilz, we have our PLC Sigma range for individual safety relays, or we have our recently launched My PLC for modular safety relays. And there's a link here where you can find more about those products. The more common way that we're seeing nowadays is to wire into individual inputs, native inputs, outputs on the safe software configurable safety controllers. And we have our PLC Multi-2. So we have either our MB0, which has got 20 inputs, 4 outputs, and you can have up to 6 additional IO cards, or alternatively, you can have our MB1, where you can have up to 12 additional IO cards. And again, there's more information on these links here. You can zone fault-free switches into small groups. So individually wired guards or zones as below using our PDP-20, which has test pulse outputs, OSSDs, which is output signal switching device. This avoids the need to rip out existing switches by monitoring those individually via a 4-way gate array, and you can link those back to one safety relay. So they look, these are the units here, they look like a safety relay, but they have 8 input channels that monitor up to 4 switches. And as long as all channels are healthy, it gives you an output that can be wired back to another PDP unit, which can then be wired directly to the safety relay. So instead of removing all your existing volt-free switches, you can add these PDP-20 units to your machine, which will minimize the change over of switches, reduce your cost of cabling, and improve safety up to PLE per switch, as they have 99% diagnostics coverage. So individually wired volt-free contacts back to interlock switches, e-stops, with a PDP-20. They use these test pulses, T0 and T1, on each dual channel device for short circuit detection and check simultaneity and has test pulse outputs, which can cascade to other PDP 20 units. So how does this work? So here are our two PDP 20 units, X1 and X2. X1 is looking at the 4 individual switches to make sure they're healthy, and the output is going to another input of X2, which then has 3 switches wired to it. The output of which is OSSDs, is then going into the safety relay, which is then used to control the main access on the machine. And they can be used for all volt-free switches, such as interlocks and e-stops. This is an example of how it would be wired. They have very high impedance, which means that PDP-20s can be used to cascade over hundreds of meters on or within a panel as a digital input expansion. So what we have is, this is our XP1. These are our 4 individual switches, and these are the test pulses. And if everything is healthy, then it will output into X2, and that will monitor the output of X1 and the 3 additional switches with the test pulses. And if they're healthy, then it will output to the safety relay. Finally, interlocking with integrated fault detection. So if a series of interlock switches is required to meet PLE, using switches with integrated fault detection can overcome some fault masking. Interlock devices featuring OSSDs outputs with microsecond off-pulse fault detection and inputs with plausibility cross-checking built in are unaffected by fault masking. So what we mean by that is this switch is checking the output of this switch, etc. It's an RFID frequency. There's no internal moving parts, so it's rated at IP67 or 69. And the temperature range can be from -25 to +70 degrees, and ATEX is also available. It comes in different shapes and sizes depending on the application, and the actuator can be mounted in various positions or forms, again to suit the application. And we've also released the world's lowest profile actuator, which is 18 millimeters in diameter and just a 3.8 millimeter depth. And this is retained with an adhesive, and if you were to peel it off, then it would destroy the actuator so that it can't be used. So although performance level is unaffected, reaction time should be considered carefully when using these devices. Each safety switch has an intrinsic reaction time or risk time, and for Pilz, our maximum is 260 milliseconds. So each safety switch also has a delay on de-energization time or propagation time to process the incoming OSSDs from the previous switch, and for Pilz, that's 20 milliseconds. The function of the furthest away switch has a resulting reaction time equal to its own intrinsic reaction time plus the sum of the propagation times of all the switches and safety relay downstream. And so an example of this is, again, here are our 4 switches, here's our safety relay. If we look at switch 4, total reaction time for switch 4 safety function equals the reaction time of switch 4, which is 260 milliseconds, times 3 delay inputs of each switch, which is 20 milliseconds, plus the reaction time of the safety relay. So effectively, that's the 260 milliseconds plus 3 times 20 plus your 20 milliseconds. So in total, that's 340 milliseconds. And this needs to be considered for the safety distance between that end line guard 4 switch and the hazard, in accordance with the following calculation, which is S equals K times T plus C, which is taken from 13855, where S is the minimum distance from the hazard in millimeters, K is the human approach speed, T is the total stopping time of the machine, and C is an additional distance based on the device topology used. So our types of RFID devices with OSS D outputs and cascading inputs, we have the PCN code, we have our PCN S-lock, which is a process solenoid lock with built-in RFID guard position monitoring. We don't advise this for personnel applications because this is powered to lock. So if power is removed, then the locking function is no longer there. We have our PCN gate, which incorporates command to release, e-stop. It has an emergency escape from inside the hazard area, and again, RFID monitoring. And then finally, we have our PCN M-lock, which can be up to performance level PLE, and you can use this in conjunction with our PCN gate box, which can incorporate, again, the e-stop and reset push buttons, etc. You can also distribute fail-safe inputs into safety relay via passive IP67 rated input modules. So the Pilz PDP67 units operate with 8-pin OSSD based safety switches, such as our PCN code RFID switch and the PCN S-lock, and they're effectively series connection boxes. So what you can do is link all your switches into the PDP 67 module. That can then be inputted into another PDP module with additional switches that can then be outputted to your safety relay, and you can also output the status of each one to your PLC. Alternatively, you can connect distributed fail-safe inputs into programmable safety relays, such as our PNOS Multi-2, and that's via an active 67 input module. So these PDP 67 modules can be used with all safety sensor types, so contact-based or OSSD types, and the PNOS Multi using an IO-NetP modules, which is what you see here. The benefit of this is a high level of safety, up to PLE SIL 3, long cable runs up to 1,000 meters, reduced field cabling, panel space, reduced installation time and cost, rapid commission and fault finding, and future expansion on modular machines. And here, the output of all these is cascaded into the input of the following PDP unit, and we can output this to a HMI, so you can actually see what's happening on each switch. So an example of this would be a PNOS Multi-2 base unit with up to 4 PDP link modules, then up to 4 PDP 67 field blocks per PDP link module. And you can have, so potentially you can have 64 dual channel sensors, and where voltage drop may occur, you can have extra power, so that may be because you use a light current, for instance, which generally uses a bit more power. Then we can provide our PDP 67 HV version to accommodate that, and you can provide it with additional juice power. So if we have a large number of safety inputs over long distances, then we can use a safety PLC and remote IO, and so we can decentralize extremely large numbers, so hundreds to thousands of safety input circuits using IP20, IP67 remote IO, such as that found in our PSS 4000 system, and we can distribute that using safety NetP protocols. And this can either be done over Ethernet copper cabling limited to 100 meters, or over copper and fiber optics cable using fiber optics and network switches. So the table that we see here is table 1 from 14119, and this provides an overview of interlocking types with a cross-reference to the examples to the standards in the annexes. And so we have the actuation principles. So these are mechanical, and they can either be physical contact or force, and they'll be either uncoded or coded, and we'll go into that in a bit more detail. They can be non-contact, so by that the principle would then be inductive, magnetic, captive, ultrasonic, optic, and they're all uncoded. And type 3, or they would be magnetic, RFID, or optic, and they can be coded and classed as type 4. So examples of this would be a mechanical cam or hinged interlock would be type 1. You can see an example here, and this is direct acting. So the force of the cam is putting direct acting on the plunger itself, which will activate the switch, and that will be the same case with the hinge in the hinge type. We have tongue-shaped actuators or trap key, and these are coded, and these are classed as type 2. And so what we mean by coded with the tongue is that the tongue itself is coded. So it's the shape of the tongue that actuates the switch in device. And so you can't just use a screwdriver, for instance, shove that in the end of the switch itself to activate the switch. And for trap key, that's typically done with the key, again, whether that's a linear or a rotary key, but that key code would activate the corresponding part of the trap key system. We have, for non-contact, we have inductive, captive, capacitive and optic, and these again are uncoded, and these generally are not safe enough for interlocking guards due to the lack of coding, and these are bypassing because you can simply just put a screwdriver or a metal plate in front of this to detect that something is in the vicinity. And finally, we have magnetic and RFID, and these are coded switches, type 4, and these are just some of the range that we have here, which I'll go into more detail. And so the level of codings, we have low level, for which there's 1 to 9 variations in code available. We have medium level, of which there are 10 to 1,000 variations in code. And we have high level, for which there's more than 1,000 variations available. And an example of that really would be high covers uniquely coded RFID systems. Medium generally covers trap key systems and some limited RFID systems. And low covers magnetic read switch types and reteachable RFID types. So defeating safeguards, manipulation. So ISO 14119 stipulates that the machine shall be designed in such a way that it minimizes the motivation for defeating the interlocking devices, and goes on to stipulate the interlocking device shall provide the minimum possible interference with activities during operation and other phases of the machine life in order to reduce any incentive to defeat it. So why is this important? Well, a report was carried out by a German test house, and its findings were that 37% of safeguards are manipulated constantly or occasionally, and that 25% of all accidents when operating machinery can be attributed to manipulation. So a quarter of all machinery operating accidents were caused by manipulation, which is quite staggering. So design measures are implemented to minimize defeat, and have become a large and important part of 14119 standard. And this was the result of authorities observing that interlocking devices are a likely safety element that can be easily defeated if the design is not done properly. So motivation for defeat, therefore, should be normally be assumed. And as a result of the more stringent requirements of the standard, additional measures often need to be applied. So this would typically lead to the requirements of attaching at least an actuator in a non-detachable way, for instance, and that could be via welding, gluing, riveting, etc. And so this is a kind of a process chart to look at ways of minimizing defeat, and we'll run through this over the next couple of slides. So 7.1a, use of basic measures. So we need to look at basic measures when selecting interlocks. Make sure that the fastening is adequate. The forced opening leads to a reaction, so that could be a temporary restart, for instance. The device must be able to withstand expected forces, and dynamic effects such as bounce must be considered. And type 3 interlocking devices are not ideal because they can be easily defeated and have no coding, so avoid them for interlocking guards. Uh, 7.1b, check whether there is a motivation to defeat in a reasonably foreseeable manner under various modes of operation and document. So this chart here will give you various modes and tasks, and you can use this really to evaluate the motivation to defeat the interlocking devices on the machine. .1c, check the extent to which the motivation can be eliminated or minimized. So if there is a motivation to defeat, can we minimize it really or eliminate it? So we look at the design measures, but we then also look at alternative operating modes. And note, motivation to defeat can be avoided by implementing alternative operating modes. And for Pilz, this could be using something what we call a PIT gate box with a PIT reader. And so if you want to have different operational modes for different operators or personnel, could be a cleaner as opposed to the machine operator itself, then we can use this device here with an RFID coded key, and that would give different personnel different authorization to access machines in different ways. Alternatively, you could use a PIT-enabled switch, and that would allow an operator to work safely within a machine dangerous area. It may be that you need to put the machine in a inch mode, for instance, but you're doing that whilst in the guarded area. And if there was an incident, the way that it's designed is that you would release the switch that would stop the machine. You could do it via encoders to determine safe position and speed. 7.1d, additional measures are required if defeat in a reasonable foreseeable manner remains. And so if the possibility of defeat cannot be excluded through modified or additional operating modes, only one element really remains for the design engineer, and that's to make it more difficult or impossible to defeat the interlocking device. And so prevent accessibility to the elements of the interlocking device by installing them out of reach, using barriers or screens, or installing them in a concealed position. Number two, prevent substitute actuation of the interlock device by means of objects that are readily available. So again, what do we mean by that? And this really goes onto the codes, the low, medium, and high. So you can't just go and get a screwdriver out your toolkit, for instance, and bypass the actuator in the switch here, or you can't just put it to bypass the type 3 switch that we see in this position. So that's why generally they're low. If we look at our PCN code and our S-lock, M-lock, and gate lock, these are available either in low or high coding. And for Pilz, we call them either coded, fully coded, or uniquely coded. And what we mean by that is a PCN code coded switch means that we'll supply you with this switch and the actuator coded, but if the actuator fails, you can just purchase a new one and use it with the existing switch, and you can do that with no problems. If it's fully coded, then again, we'll supply you the switch and the actuator, but if the actuator is to fail, then you can replace it up to 8 times. Once you've replaced it the 8th time, it will then make this switch redundant. So you'll have to throw them both away and buy another set. Or we do uniquely coded, which means that we'll supply you the actuator and the switch as a coded pair. So if either fails, you need to buy a new set. Number 3, use of caps or permanent fastenings. So this is where we talk about welding, sticking, one-way screws, rivets, etc. So as a manufacturer, Pilz can supply you with caps for our switches and actuators. And so here's the PCN code. These are the kind of caps that we can supply, and that will hide the screws and secure them in place. We do stick-on actuators, which was kind of mentioned earlier. So if these are peeled off, then the actuator itself would be destroyed. We have the one-way screws, which are available. And then we also do M12 connectors for anti-tamper brackets. So again, if this is your PCN code, this is your cable, your screw-in cable coming in and connector, we can then put this over the top so that you can't just unscrew it basically from the switch itself. And prevent defeat by integrating monitoring of defeat within the control system itself. So that could be status monitoring, or you can do periodic tests, and you can use the real-time clock on the safety controller. And for frequently open guards, ISO 14119 stipulates a test pulse once a year for PLD and once a month for PLE. Excuse me. And what we mean by that is that if the gate hasn't been opened within a month for PLE, then the safety relay would prevent restart of the machine unless you went to actually test it. So the use of fault exclusions and how to achieve PLE interlocking and guard locking. So the use of fault exclusions has long been covered in EN 62061, and it's also covered in 13849 Part 2. And Annex D, Part 8, states that a single mechanical point of failure, that's all that cannot be fault excluded for PLE by the user. And this limitation to PLD for fault exclusion appears in ISO 14119. And fault exclusion on the tongue can be made using what we call our PCN bowl. And this is a PCN MEC 1 or 5, so a tongue actuated switch, but it also comes with a PCN code, an RFID switch. So if you were to open the gate and the tongue was to break, for instance, or was to be dislodged within the switch itself, then the RFID switch will break, and that would send out a fault to the relay. To achieve PLE, especially for guard locking, the use of at least 2 devices is necessary unless the user uses a PLE certified guard locking interlock device, where the manufacturer states maximum extraction force, and in Pilz case, the interlocking is done electronically, and we do this via RFID in the tongue. So the tongue itself has got RFID inside it, and the solenoid is bistable, so it's pulse to lock. So it's bistable pulse to lock, and it's pulse to unlock. And we do that in both our PS gate lock system and in the PCN M-lock. So how do we select an interlock really for guard locking? So we look at the overall stopping distance. Oh, sorry, though. We look at the overall stopping performance, so the access time. And so if the machine has a rundown time, then we need to take that into account. And we would refer to what was discussed earlier, 13855, to work out the stopping distance. But if there isn't one, then we can interlock the guard without guard locking. That's sufficient. And in that case, you can use either a tongue actuated switch or a coded switch to send the output signal back to the safety relay to stop the machine. If there is a rundown time, then we'd need to interlock the guard with guard locking. So that means you'd have to request access. And so here we have our pit gate. We'd press a button to request access to the machine. That would send a signal to the machine. Once the machine's stopped, that would then send an output to allow release of the actuator so you can gain access. And then only once you've closed the door could you then restart the machine. And then what was discussed earlier was the maximum static action forces. This is in Annex 1. The manufacturer of the guard locking device shall ensure that in the engaged position, the guard locking device withstands at least the specified holding force F. The manufacturer shall specify a holding force which shall be less or equal to the holding force, and that must be really at least 1.3 times the force. And so what we can see here on the chart is if you were sitting down and pulling the actuator horizontally, the force value is 600, and so you should have 1.3 times that amount as the manufacturer on your interlock. These are our typical values for our interlocking devices, but just to note that what was said earlier, the S-lock is really for process, not for personnel, as it's energized to lock, and so it would fail in the loss of electric power. And then to run through on this slide, really a selection of our interlocking, powered interlocking devices. So the applications for all of them really can be covers, flaps, swing gates, and sliding gates. Apart from the PSEN gate, that's typically used for large accessible swing gates and sliding gates. And the functional principle really are electromechanical for the PSEN MAC, and then for the remaining items they're all a transponder. The guard locking principle, again for the MAC and the S-lock, they're normally de-energized mode and normally energized mode, whereas to achieve the PLE for the M-lock and the S-gate we have bistable principle. The safety functions for all are either personnel protection or process protection, apart from the PSEN lock, and the performance classification for PLE for all apart from the PSEN MEC, which can be to PLD with a fault exclusion. And then we stipulate the holding forces, so that's anywhere from 1500 newtons up to 7,500 newtons for the PSEN M-lock. And then we have the manipulation protection that we ran through, so ranging from low up to high. And then we can provide these with X-gate releases if necessary. So if you were to walk through one gate and that the access out was blocked for any reason, you needed to go out of another gate, then we can provide crash out systems to allow that via the either escape or emergency release. So a new version of 14119 has been on the cards for a little while, and really some of the main changes within that will be that trap key systems are potentially going to be classified in their own specific group. So where they're listed as type 2, they will become type 5, and there'll be far more detail on trap key systems. So as it stands, there's probably about a paragraph, 2 paragraphs within the standard itself. So there will be a lot more detail, and there's been a lot of input from trap key manufacturers, as you can imagine, as to how those systems should be manufactured and operated. And there is further guidance on fault masking scenarios, which will be included within 14119 itself, not separately within the technical report 24119. And when that standard is finally released into the domain, then we'll run another webinar based on that revised standard. So really, all that leads me to say is thank you for attending today. All previously recorded webinars can be found at our GoToStage channel, which you can view here. And there'll be previous topics there from cyber security, CE marking, Pure 13849, etc., etc. The next webinar that we have is understanding 13850, which is emergency stop functions. And I've not put the date there, but that is towards the end of next month, May. And all future webinars can be found on our website below. So thank you all for attending today's webinar. I hope you found it useful and informative. And yeah, all that leaves me to say is have a great bank holiday weekend, and we'll catch you next time. Thank you.